Okay, this is a walkthrough of a free body diagram problem, and this will use pushing forces, pulling forces, and friction forces. All right, so let's say that we have an incline and a block on the incline with a mass of 10 kilograms. And this block is attached by a pulley to a hanging mass. The hanging mass is 5 kilograms. And let's say that the coefficient of friction between the block and the contact is 0.2. And at the instant shown, the system is moving this direction. So the block is sliding up the ramp and the hanging mass is moving down. Okay, so we want to draw free body diagrams of both of these two things. Let's start with the hanging mass. That's definitely the simpler one. So first draw an outline. Now think for a second, what's the first force that we always apply in a free body diagram? That's the weight force. And so that is always downwards, no matter what kind of motion you have. And that's the mass times 9.81 meters per second squared. So in this case, that's 49.05 newtons. And the next step is to go around the boundary looking for anywhere the surroundings make contact. So imagine going around the boundary of this and identify there's only, in this case, one place where the surroundings make contact. Where is that? That is right here. And now you have to ask yourself, what kind of force is that? So that contact point is going to apply a force. Is it going to be a pushing force, a pulling force, or a friction force? Well, this is a cable. Cables always apply pulling forces. That's all they can do. Pause the video for a second and see if you can figure out how to represent that pulling force at that spot. Okay, so that will be parallel to the cable, away from the body, and we'll give it the variable t. And now we'll go to, that's the complete free body diagram of that one. And we know that it's a complete free body diagram because there's nowhere else around the boundary that the surroundings have made contact. Okay, so now free body diagram of the 10 kilogram. So draw the outline. And it's worth being careful about these angles. You always want to be able to show in your free body diagram what things are parallel, what things are perpendicular, and what things are neither of those. Okay, so even if this was at a 5-degree angle, doing this at exaggerating that angle a little bit makes it easier to make those angles obvious. Okay, so first, what's the first weight that acts on that? Pause the video and apply that. Okay, so the first thing is always the weight. That's the mass times 9.81 meters per second squared. So in this case, that's 98.1. And now go around the boundary and identify any places where the surroundings make contact. There's contact at the ground, and there's contact here. And that's all there is. So we know there's only two contact forces that we have to deal with. Let's start with this one over here on the left. Pause the video and see if you can identify what kind of force that is, and then show it in the free body diagram accurately. Okay, that's a cable, so it's a pulling force. So the rule says that force is parallel to the cable, away from the body. And since it's the same cable as this one, the magnitude is the same, so we'll give it the same variable name. So whatever T is, when we solve it, it's going to be the same in those two cases. And now this contact force with the ramp, pause the video and see if you can identify what that is and represent that. Okay, that is a friction contact. Friction contacts are always broken up into two things, a pushing force and a friction force. The pushing force is always perpendicular to the surface toward the chosen body. And I'll give that the variable name N. And then the friction force is always opposite the direction of motion. Since the motion of this body is up the ramp, the friction force is down the ramp, so like that. And the magnitude is always equal to the coefficient of friction times this normal force. Okay, so remember that's not newtons. That's you're multiplying 0.2 times whatever this pushing force is. That's because the friction force, the friction increases as the object is pushed harder into the surface. Okay, so that's a complete free body diagram of each of those two.